In this screencast, we'll take a look at the differences between the inherent characteristics of valves and the installed characteristics of valves, why they're important, and how to conduct a calculation with them. So the inherent characteristics represent the characteristics of the valve really as if the valve was by itself. In other words, minimal piping and no other unit operations. And the important part about this, in terms of the valve equation, is that delta P is a constant, regardless of the amount of flow going through your control valve. This would really represent buying it off the shelf and just running the valve. The problem is that oftentimes when we're going to want to use control valves or valves of any kind, they're not just going to be by themselves in a little bubble. They're going to be in line with potentially long amounts of piping, various unit operations such as heat exchangers and reactors and separators and the like. Because of the presence of these other unit operations, the way the valve acts by itself is not going to be the way it works when it's put in a process, and that represents the installed characteristics. And the important issue with the valve being in a process is that delta P is now a function of your flow rate Q. When you have a system, your fluid is going to start at some particular pressure, let's say 5 psi, and then it's going to end at a separate pressure, let's just say 1 psi. And it's open to the environment. So therefore, as it goes through, it's going to go through a pressure drop. And this pressure drop can be caused by friction losses of some sort. These friction losses can come from the various pieces of equipment. If I had just a control valve in this start to end, the valve would take the entire pressure drop. So therefore, inherently, the delta P for the valve would be 4 psi. However, from an installed standpoint, the pressure drop would most likely be less than 4 psi because it goes through other pieces of equipment, heat exchangers, etc. The pressure is going to be dissipated because of other aspects of a mechanical energy balance, with one example being friction, also velocity changes, etc. Another important issue here is that inherent characteristics and installed characteristics have a great effect on the selection of the valve that you use. So if we look at our two common types of valves, linear valves and equal percentage valves, the definitions have been established for systems with a constant pressure drop. So therefore, for a linear valve, the flow rate is directly proportional to the lift, and for equal percentage, it is related such that there is an equal percentage change in flow for a change in the lift, which represents different things. But the question represents is, which one do we want? We desire to have a valve that has a gain that is as close to constant as possible. So what we would want to have here is we would want either dFdL, where F is the valve characteristic, or that dQdL, where Q is the flow rate, is approximately constant. F and Q are proportional to each other, just remembering the design equation for a control valve. So at first glance, this looks like our choice is really simple, because by definition, linear valves have their flow rate directly proportional to the lift. So therefore, dQdL there will always be a constant. That is only true for the inherent valve. Therefore, if your system is operating such that your pressure drop across the valve is either constant or approximately constant, then you're going to want a linear valve. For processes where the pressure drop across the valve is not constant because of the installed equipment aside from the valve, what's shown to happen is that the equal percentage valve, which by nature is nonlinear for an inherent system, becomes much more linear for an installed valve. So to see this difference between inherent and installed characteristics, we will look at a system where we're trying to flow 200 GPM of water through a control valve with a particular CV, and we want to see how open our valve needs to be for both a linear valve and an equal percentage valve for two situations. One, where we have a pressure drop of 10 psi constant, independent of the flow rate of water. And then we have one where the pressure across the valve can be represented by the function provided, which shows delta P as a function of Q. So to do this, we can start with the valve equation here and recognize that our goal here is to find the openness of the valve. And the openness of the valve is the lift, represented by a cursive L, And this is related to the valve characteristic F. We're going to want to solve for F, and this will leave us with F equals Q over CV multiplied by the square root of GS, the specific gravity, divided by the pressure drop across the valve. So for a linear valve, F is just equal to L. So for the linear valve for part A, we can just note that L will equal Q over CV multiplied by the square root. And here our flow rate is 200 GPM. We have our value for the valve of 110 GPM per PSI to the 1/2. And then we have the square root of the specific gravity, which for water will be 1, divided by the pressure drop across the valve, which is 10 psi. And when we do this, we find that our valve openness is 0.575. We can do this exact same equation for part B, but the only difference here is that the pressure drop has changed. So instead of it being 10 psi, it is now 10 minus 0.03 times 200. We end up with 0.909. So therefore, in our case here, the valve has to be much more open for this, mainly because of the fact that there's less of a driving force present because of the reduced pressure drop, which if we were to do the actual calculation would represent that our delta P is now 4 psi. Let's do analysis for the equal percentage valve. The major difference here is that F does not equal just the lift. In fact, it's a relationship of R raised to the L minus 1, where R is just a parameter of the equal percentage valve, which is usually somewhere in the range of 20 to 50. So if we wanted to use this equation, we would have to say that R raised to the L minus 1 equals Q over CV times the square root of GS over the pressure drop of the valve. What we then do is take either the natural log or the log of both sides. Here, taking the advantage of the rules of logs, we can write this as L minus 1 log of R equals the log of Q over CV times the square root of GS over delta PV. After doing some relatively basic algebra, we can solve for L as L equals 1 plus the log term we just had on the right divided by the log of R. For this analysis, we'll assume that R is 40. So for part A, when the pressure drop is 10, we'll have an answer of 0.850. For part B, again, remembering the fact that here where delta PV is now equal to 4, without showing the math, we end up with an answer of 0.974. The valve is much more open for the equal percentage case, which makes sense based on the definition of how an equal percentage valve works. But you'll also notice the fact that the difference between the lifts in part A and part B is much less significant in the case of the equal percentage valve versus the linear valve. So to determine which one of these valves is of interest, what we would need to do is not just focus on one flow rate, but focus on trying to find pairs of the lift and the flow rate for a variety of flow rates. And when trying to select a valve here, our two criteria would be: 1, is the valve gain relatively constant over the flow range of interest? And 2, is the valve nearly fully open or fully closed over this range? The reason why 1 is important is because if the gain is not that constant and gets too large in places, what will happen is the flow can tend to oscillate, which means that small changes can lead to very large flow rates. However, if the valve gain gets too small in comparison, what this means is the fact that the process will be sluggish because it won't be able to respond as quickly to changes because of the size of the gain. Additionally, you're going to want the valve to be away from being fully open and fully closed. The reason why is because of the fact that the valves don't operate as well from a reproducibility standpoint when you are on the edges, whether it be too closed or too open. So what we're going to do now is show a graph of how these systems work both from an inherent standpoint and an installed standpoint. So if we look at the graph of these flow rates versus lift, what you'll notice here is that A is a very big difference between the inherent and installed characteristics of both valves. The dashed lines representing the installed characteristics for both, and we have the blue representing the linear and the red representing the equal percentage. And what you see is a very big difference in their trajectories. Another important difference to realize here is the fact that the linear curve has become much less linear and has a significant amount of curvature to it. And similarly, what we see with the equal percentage curve is we go from inherent to installed is we actually see the fact that the curve has flattened out a bit, making it more linear. So therefore, this shows that in some situations, we would actually choose an equal percentage valve because of being in this more linear range. So if we look at where we're interested in, we're interested in the flow rate of approximately 200 GPM. And what we see here, this valve CV value is a very poor choice once this is installed. The reason why is the fact that in both cases we're operating very close to a fully open valve, something that we found by carrying out the earlier calculations. Therefore, if I were to choose a linear equal percentage valve here, I really wouldn't aim for either one because we would want a different valve. We would want a valve with a higher CV value, one that would allow for a higher flow rate to go through, which, if you recall, the definition of CV represents in the units of GPM per PSI to the 1/2, it represents how much water flows through a valve when it is fully open and the pressure drop across the valve is 1 psi, with the fluid being water. So here you'd want to choose a higher CV. But also, if I look at this, aside from that, is I'm in a range with the equal percentage valve where I'm actually relatively quite linear and not terribly flat, two positive things in terms of selecting a valve. Whereas for the linear installed, since the slope is so small, it would be a bit sluggish to respond because in order to make a change in flow rate, it would involve a significant change in the valve. You have to be very careful in how you select a valve because, for example, in both of these processes, if I'm running it with the aforementioned process where I have that delta P relationship, these valves will be unable to handle flow rates much greater than 200 GPM. So therefore, if this process can fluctuate, say, between 150 and 250 GPM, this can cause significant problems for your process, mainly because caused by the pressure drop issue. So this screencast, hopefully we showed the importance of inherent versus installed characteristics and how that can be really important in terms of selecting the type of valve you want to use for your process, both from a CV standpoint and from a linear versus equal percentage standpoint.